trouble on last night's homework. So if you want to hang out for a little bit after class, I'll be glad to go over that with you. Or if we have time, I'll do it before class ends, but I don't think I'm going to have time. So I'm going to do a real quick little overview of logs, and then we'll do a little short Kahoot on the basics, and then we'll jump into the bookwork for log functions on 5.4. And then tomorrow Matt's going to do all the properties of logs, and then we'll take Thursday for a kind of stop and go back over everything we've done. And then, like I said, Friday we'll do the go over last week's test. The bookwork, as I was filling it out to get ready to grade y'all's bookwork, the written work doesn't really match the bookwork. It's not, it follows through, you know, if you've paid attention to the notes, it follows along, and you can probably analyze it and figure it out. But so I really do want you to try it on your own. It's good stuff, but it doesn't really match what we're doing today, like identically. So if you are having trouble on that, we can go over it on Thursday as well. Or Matt can go over it again on Wednesday if we have time. So reminders, final part 1 is on Wednesday, December 9th. And this part of the final will mainly cover the material we're doing on logs and exponents. It might have a few things on inverses that actually apply to what we're doing right now, but we will have a review for it. So you'll see, you will not be, there'll be no surprises. Then the second part of the final is Friday, December the 11th, and that's the comprehensive part of the final. It covers mostly stuff, the college algebra part of the class. So there are reviews for both part 1 and part 2 that are up on Blackboard right now. So if you want to just kind of look it over, that's great. But they are both subject to change a little bit as we go into next week, especially for part 2. Probably will change somewhat. Okay, so I did put this little log cliff notes on to Blackboard under the notes if you want to have a copy for yourself. Otherwise, just follow along with me on this. Okay, so a logarithm is the inverse of an exponent. It's just really another way of writing an exponent. So for example, if we look at, and I'm going to go through this fairly quickly, 5 to the second, we know that that is 25. So 5 to the second is 25. That translates to mean the exponent, which a logarithm is just another word for exponent, that turns 5 into 25 is 2. And sometimes we have to refer to these parts of this. This is the base of the logarithm. This is the argument. And this is the exponent. Okay, so we know 2 to the third is 2 times 2 times 2 is 8. The exponent is 3. Another way to write this is the exponent that turns the number 2 into an 8 is 3. So 10 to the 4th, we know is 10 times 10 times 10 times 10, which is a 1 with 4 zeros, 10,000. 10 to the 4th is 10,000. Another way to write this would be log base 10. The exponent that's going to turn 10 into 10,000 is 4. Now, this right here, log base 10, we use it so often. It's called the common log. that we don't usually write that base. It's not incorrect to write it, but we don't usually write it. We just usually write this as log 10,000. And actually in science, they call E the common log, ln, but in mathematics, or at least in this book, we call it base 10 the common log. So every time you see a logarithm, just ask yourself, you're looking for an exponent that turns this subscript into this 9. And again, if you're a sloppy writer, where we put these numbers really matters. The subscript needs to go down below and it needs to be a little smaller. A superscript needs to go up above, it needs to be a little bit smaller. It makes a difference. So real quickly, what would log 416 be? If you're thinking about this, what would the exponent be that would turn 4 into 16?
2.
That's all you have to do. Say 4 to what power equals to 16. So here, what would the exponent be that would turn 3 into 27? Three times 3 times 3 is 27. So what would the exponent be? It would be 3, right? So we're just looking for an exponent. Whenever you're asked to find a log, you're just being asked to find the exponent. So what's the exponent that turns 2 into 16?
Four.
Yes. That's all we're looking for. Anytime you're asked to find a log, you're just looking for the number. Now, sometimes we get a little tricky. So like I'm asking you here, I'm going to say 4 to what power is 1 over 16. Okay, so remember that to get a fraction, what kind of exponent do we have to have in order to get 1 over something?
Negative.
So whereas here log base 416 is 2, log base 1 over 16 would be negative 2. And then here, log base 1/2, I don't know why I capitalized this log, who knows? 4. So I'm saying 1/2 to some power equals to 4. How do I get that 1/2 to flip?
Negative exponent.
So it's going to be negative 2, right, as well. This would also be negative 2. All right, now this one, log base 8(1). Think about this, 8 to what power equals to 1? What's the number that makes any number the number 1?
0.
0, yes. So anytime you see this, if you ever have a 1 right here, it doesn't matter what the base is, you're always going to come back to 1. Okay, so the most used logs are base 10 and base E. And we use them so much they have their own buttons on the calculator. Log base 10 is just the log button. And log base E is the LN button. So if you just see log 35, for example, that means log base 1035. And all you have to do on your calculator is just type the word log. Make sure you can find these on your calculator. They're on the, most calculators, they're on the left-hand side. So if you type log 35, just type it straight into the calculator, you should get 1.544. Make sure you know how to use your calculator. Do not wait till the day of the test to realize that you're not sure how to use your calculator. And then LN 35, you just hit LN and 35, and that's base E, it would be 3.555. So now without a calculator, you should be able to do any power of 10 just by counting zeros, okay? Because this is like saying log base 10, 10. In other words, 10 to what power equals to 10? So anytime you have a log and a base 10 right next to each other, they basically undo each other. So log 10 would be what? If you count the zeros on the 10, what would it be?
1.
1, right. 10 to the first power is 1. What about log 100?
2.
2. Log 1000?
3.
3. Absolutely. Okay, so anytime you have a base 10 and a power of 10, you just count the zeros. And that's because 10 to the third power is 1,000. Log 10,000 would be 4. Now here, log 1, anytime you're taking the log, no matter what the base is, if you have a 1, what is the exponent that turns any number into 1?
0.
0. All right, now sometimes you'll see some things like this, log 1/10, which is the same thing as log 0.1. This time, what kind of exponent would we have in order to get a 10th? What's going to change about the exponent?
Negative.
Negative. So log 0.1 would be -1. Log 1/100 is just the same thing as log 0.01. That would be -2. Log 1/1000 would be -3. So if you know that, that really simplifies your life a lot. If you just realize anytime you have a log on a power of 10, you can just count zeros or count the numbers past the decimal. Okay, so let's do a quick Kahoot. And again, I will give extra credit to those of you that are participating in this. Logarithms are really kind of fun, and you'll see the value of them very quickly. They are so applicable. They're not something that you see once and will never see again. If you're in any kind of business or scientific field, you see them all the time. They're very useful. Okay, try to get on, but if you can't, please follow along. As always. Go ahead and start it. Nice. Okay, it is the inverse, which is really nice. So if you know how to graph an exponential function, then you can easily graph a logarithmic function just by switching x's and y's and changing the asymptote. So then we'll be looking at that. What is the base? Okay, so remember the base, if you have a log, the base is the little subscript that is usually right after the word log. It's a little number that's just a little bit below the baseline. If there's not one there, it's always base 10. Yay, yes. So you notice it really is important where these numbers are. I mean, it makes a difference whether it's a little below or a little above, the sizes, that all makes a difference. Okay, so again, if you have a log, L-O-G, with no little subscript, that's base 10. If you have ln with no subscript, that's base E. Those are the ones that we use all the time. And people got lazy and didn't want to have to keep writing those subscripts, so they just dropped them off. You like my logs?
Are they natural logs?
They are natural logs.
We go over this in the next chapter as well, too. It's like
You're
4 properties, I think, is mainly what they do. And then they do give them the change of base formula.
Mm-hmm. So anytime, no matter what, if you're log of 1, no matter what the base is, it does not matter, is always 0. Because anything to the 0 power is 1. Okay, so if you think about this, remember a log is an exponent. So we want the exponent that turns an A into a C. So that's how you write this. The exponent that turns the A into a C equals B. So what it equals to always, the log always has to equal to the exponent. The base is the number that has the exponent on it. And then the B is what it's going to equal to. And the C is what's being changed. I know that sounds confusing. Okay, on this one, pick any of this one, think about it. Pick all that are correct. Okay, so all four of them, and if you think about this, okay, so if you have log base AB equals C, that's the same thing as saying A to the power of C equals to B. Well, A has to be a number bigger than 0 because let's say you have -2 to a power. If you have -2 to the first, that would be -2. If you have -2 to the second, that would be +4. And you'd be bopping back and forth between positives and negatives all day, and that's not gonna work. So that's why A has to be positive. But C can be anything, positive or negative, because if you take a number to a negative power, you can get anything. It's going to be all real numbers. B has to be greater than 0. I mean, the exponent can be anything. B has to be bigger than 0 because no matter if you take a positive number to any exponent, you're going to get a value that's larger than 0. And A can't equal to 1 because 1 to any power is just always going to be 1. So that wouldn't make any sense either. And basically, these become important when you're trying to solve an equation, which you'll be doing later on. Okay, so remember, if you have log, the base here is 10, even though it's not written. And anytime you have the log of a power of 10, all you have to do is count the zeros. So it would be 6. So I'm not sure if that hint was really that helpful. A lot of people just like to look at it as the reciprocal of 10,000, in which case the log of 10,000 is 4. So the log of 1 over 10,000 would be -4. But sometimes it does help to look at it as the decimal version. If you count the digits past, or the numbers past the decimal, 1, 2, 3, 4, that will tell you what number you need, and then it's negative because it's smaller than 1. If you have a log and a 10 that are right next to each other, they cancel each other out because they're each other's inverse. So this log and this 10 just make each other go away. And you wind up with 2 times 12, in other words. Yep. So the log and the 10 undo each other, and you're just left with 2 times 12, which is 24. The same thing as an L and an E. An LN and an E that are right next to each other, they're each other's inverse, so they cancel each other out. They undo each other. So that LN and that E just are going to go away, and you're just going to be left with the exponent. Good. Yes. So since that ln and that e cancel each other out, you're just left with the 2. It doesn't stay an exponent anymore. It's just like a plain old 2. And 5 times 2 is 10. So I can see where people got the 25, but that the ln and the e cancel each other out. That 2 is no longer an exponent. Okay, so I just want to remind you, this is the base, this is the argument, and this is the exponent. So if you were to rewrite this in exponential form, it would be 2 to the 3rd equals to 8. So here we have a base of 7 and an argument of 7, if those two things are the same, then they cancel each other out because they're each other's inverse. Yay. Good. That's really helpful to know. Okay, if the base and the argument are the same, they just undo each other and you're just left with the exponent, which is no longer an exponent. And the same thing holds true here. We have this base to a power that is a logarithm that has the same base. So those guys are going to cancel each other out. Good, good, good. Now here, think, what's the exponent that turns 3 into 81? Okay, so it would be 4 because in order to get 81, you multiply 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the 4th power is 81. And if you got that previous one, this one just has one little tiny change. Tiny. Doesn't make a huge difference. Good. So we know that 3 to the 4th is 81. So that means 3 to the power of -4 would be 1 over 81. Yay, Elliot. Yay, Aurora. And our superstar. All right. Good job, you guys. Olivia. All right. All right, so now let's look at the homework. What? All right, so first of all, we're looking at number 5. So what is log 10?
1.
1. Thanks, Timothy. And what about log 10,000?
4.
4. So if you have a log, remember these are base 10, even though they're not written. And it's the log of a power of 10, you just count the zeros. All right, now this is the same thing as 20 times the log of 1/10, right? So that would be 20 times what?
-1.
-1. Yep. All right, so then here we have log 10, which we already said was 1. And what is log 0.001?
-3.
-3. So that's going to give us -2. Yep. All right, now this one, 9, it says 9b, but we'll do both of them. So I think this is kind of confusing what they're asking, but it says determine mentally an integer and so that the logarithm is between n and n plus 1. Check your result with the calculator. So log 79. So what they're talking about is, for example, we know that the log of 1 is 0. The log of 10 is 1. The log of 100 is 2. The log of 1000 is 3, and so on and so forth. So the log of 79 would have to be between the log of 10 and the log of 100, right? Because 79 is between 10 and 100. So that means the actual log of 79 would be a number between what and what?
1 and 2.
1 and 2, right. It would be a number between 1 and 2. And if you check that on your calculator, if you take the log of 79, it turns out to be, so this is just like if you're doing quick mental math and you're just trying to figure out, well, what is the log of 79? You can kind of think about it that way. And it would be 1.897. Okay, so what about the log of 500? What numbers would the log of 500 be between?
2 and 3.
2 and 3. So you'd get the log of 500 would be a number between 2 and 3 because 500 falls between, log of 500 falls between the log of 100, which is 2, and the log of 1000, which is 3. And you can check that on your calculator. Okay. Now this says find the domain. So you can never take the log of a negative number, nor can you take, just the log of a negative number. So just remember that. This has to be, and you can't take the log of 0. Okay, so this right here has to be greater than 0. So the domain would be everything greater than -3. So just remember that the when you're taking the log of a number, you can never take the log of a negative number, nor can you take the log of 0. So it has to be greater than 0. All right, so this says that x is 2 to the 0. So what would the log base 2 of 2 to the 0 be? What happens when the base and the argument are exactly the same? They just cancel each other out. So you would get 0. So here, they've already done this one for you. This is just like saying log base 2 to the 4th would be 4. What about log base 2 to the negative? What is that? 8. That would just be and then here log base 2 to the 1.26 would just be 1.26. So that's just what we were talking about earlier. Anytime you have the base and the argument are exactly the same, they just cancel each other out and you're left with the exponent. Okay, so now we are on number 31. Okay, these are so simple though. I want to go ahead and do several of them. So what would 31 be? Log base 5 pi to the power of pi.
Pi.
Pi. And what about 32? Log base 6 to the 9th. Just be 9. And what about number 33? Log 3 log 3 x minus 1. What would that be? It would just be x minus 1, right? And 8 log base 8 pi plus 1 would just be pi plus 1. And then log base 264. Okay, so you're asking yourself 2 to what power equals 264, and that's going to be what this equals to. So what would that be?
Six.
Yep. 2 times 2 is 4, 8, 16, 32, 64. That would be 6. All right, and then here we're asking ourselves 2 to what power is going to give us 1/4?
-2.
Yes, good. And here we're asking ourselves, oh, don't worry about that one because I don't think we've done rational exponents, so that one's. So here we're asking ourselves 3 to what power equals 9? Two. Now here on 39, anytime you have an ln and an e smack dab right next to each other, they just cancel each other out and you're left with the exponent. What about ln, just ln e? What does that equal to?
1.
1. because the exponent, even though it's not written, is a 1. All right, log base 864, we're asking ourselves 8 to what power equals 64? Anyone?
It's 2.
It is 2, thank you. When I used to teach in person, when people used to come in my room, I just shout out, "What's log 864?" And they'd always look at me like I was nuts, but they would answer me. All right, so not that one, because we aren't working with rational exponents, but yeah, let's not do this one either. 44, no, all the way down to 46. Okay, so 47. Log A 1 over A, what would that be?
-1.
-1, thanks. All right, and what about log A squared times A to the 3rd? What would that be? What happens when you multiply? What happens to those? What do you do with these powers?
5.
5, yes. So that would just be 5. And then log 5 to the 0 would be 0. We wouldn't do this one because we're, okay, what about log base 2, 1 over 16?
-4.
Okay, so 53. So log base 2, 9 would fall somewhere between log base 2, 8 and log base 2, 16, right? So you're trying to think of powers of 2 that are above and below 9. So 2 to the 3rd power is 8, and 2 to the 4th power is 16. So log base 2, 9 would be between 3 and 4. Does that make sense? What about log base 4, 11?
One and 2.
Okay, so log base 4, yes. Yes, it would be between 1 and 2. Because log base 4, 1, yeah, is 4, and log base 4, 2, okay, so log base 4, 4 is 1, right? And log base 4, 16 is 2, and log base 11, log base 4, 11 does lie between those two numbers, so that would be between 1 and 2, yes. And what about log base 3, 36?
You mean 35, right?
I meant 35.
I got 3 and 4.
Okay, let's see. So log base 335 would fall between log base 3, 27 and log base 3, 81, right? So that would be between 3 and 4. Yep. Good. Okay. Says use the graph of f to sketch f -1. Give a symbolic representation for the inverse. So here is f. I'm going to pick some nice points on f of x. which is e to the x. Okay, so just looking at this, I can see that one of the points is 0, 1. And another nice point is 1, 3. And I can see that I have an asymptote at y equals 0. So now I want the inverse, f negative 1x. So I switch the x and the y. So instead of 0, 1, I'm going to have 1, 0. Instead of 1, 3, I'm going to have 3, 1. And instead of a horizontal asymptote at y equals 0, I'm going to have a vertical asymptote at x equals 0. And that is what my inverse will look like. And then the symbolic reference, remember that the inverse of e to the x is ln x. So f negative 1x would be ln x. E to the x and ln x are each other's inverse. Okay, these look harder than they are. There's lots of words, but don't let that throw you. On 131, it says sound levels in decibels can be calculated by this formula, where X is the intensity of sound in watts per square meter. The human ear begins to hurt when the intensity reaches X equals 10 to the negative fourth. And then it says, how many decibels does this represent? So how are we going to find that? What are we going to do with that 10 to the negative fourth?
Plug that in for the x.
That's right. Just plug it in for X. So I'm going to say d of 10 to the negative fourth equals to 10 times log of 10 to the 16th times 10 to the negative fourth. I'm going to continue that. So that's going to be 10 times log 10 to the 12th, right? And what is log 10 to the 12th? What is this? What happens when you have a log and a 10 right next to each other?
Becomes 1.
They cancel out, right? So if you have a log and a 10 right next to each other, they just undo each other. If you have an ln and an e right next to each other, they just undo each other. So we're left with 10 times 12, which is 120. Now the question says, find how many decibels this represents. So that would be 120 decibels. Make sure you put your units in there, is your answer. Now I like this problem because I can tell y'all some personal information. It says the Richter scale is used to measure the intensity of earthquakes, where intensity corresponds to the amount of energy released by an earthquake. If an earthquake has an intensity of X, then its magnitude as computed by the Richter scale is given by this formula. R of X equals log X over I. That little 0 is like, that's the intensity, whatever you're given. And they're saying the intensity where I naught is the intensity of a small measurable earthquake. Okay. So this says on July 26th, 1963, an earthquake in Yugoslavia had a magnitude of 6 on the Richter scale. And on August 19th, 1977, an earthquake in Indonesia had an earthquake that measured 8. So how are we going to do this problem? What are we going to do? And they tell us, find the intensity X for each of these earthquakes if I naught is equal to 1. So that means basically just don't have to worry about the I naught at 1 at all. So we have basically all we have is this equation, R of X equals to log X, where R of X is the intensity. So where would we put the 6 in this problem? Would we put it in for R of X or we put it in for X?
Both?
So we're trying to find the intensity, right? Which is X. And they're giving us the magnitude, which is our R of X. So for Yugoslavia, where are we? You could say that 6 equals to the log of X. And for Indonesia, we could say that 8 equals to the log of X. And now I'm going to tell y'all my story. So I was in the second largest earthquake in history in Alaska back in 1964. It was and it had a magnitude of 9.2. And I was right in the middle of it and had some very severe repercussions from it. Anyway, so that's my interesting story for today. So now what do I do here? How do I find out what the X is, what the intensity is? What's the base here is 10, right? Even though it's not written. So this says the exponent that turns 10 into an X is a 6. So this one would be X equals 10 to the 6th. And so that would be the intensity of the Yugoslavia earthquake. And then this one would be X equals 10 to the 8th. So then it says, how many times more intense was the Indonesia earthquake than the Yugoslavian earthquake? How would I find that? How many times more?
It's 2 more. No, it's not a 2
Well,
more.
you would divide, right? Right, you got the right idea. So you would take the 10 to the 8th, which is the intensity of the Yugoslavian earthquake, and divide by 10 to the 6th. And that would give us 10 to the 2nd, which is 100. So the Indonesian earthquake
I was
is-
saying that because I know a lot of people are going to look at like 6 and 8 and say that's like 2 more additional.
Oh, you said that.
Yeah. Sorry.
Yeah, right. Y'all see, when you want to know how many times more something is, you just take the quotient of the two things, right? So
It's getting increased by 2, but it's an exponent of 2.
right,
Yeah.
right.
So it's
exactly.
100 times greater.
Right. 100 times greater.
I know there's different ways to measure the Richter scale too.
Yeah. It's kind of interesting.
Because you're talking about the tectonic plate shifting and like,
Uh-huh.
I know there's like one measurement that measures like something because some of your energy goes into the earth and some of it actually comes out into the crust.
Yeah.
So
We
there's
were on an Air Force base and literally the whole base fell down around us. It was horrifying. Anyway, so we have a few minutes. So what I'd like to do is, first of all, I know someone had a question about last night's homework assignment. So do y'all want to look at that maybe? And then I'd like to look at tonight's homework assignment and just kind of talk through it. So let's see. The question on last night's homework assignment was on number 2. So I'm not going to do it, but let's talk about how you would do it. It says an investment of 5,000 is to be invested for 5 years. First part says, what will the value of the investment after 5 years from 4.2% interest compounded continuously? So what formula would you use here? We have the choice of if it's compounded continuously, you're going to use the PERT formula. And otherwise, you're going to use the compound interest formula. So the only time you're going to use the PERT formula is you see this word continuously. Okay, so the PERT formula is always the nice one because you don't have to worry about nearly as much stuff. So here, this is the starting amount. This is the ending amount. This is the interest rate as a decimal. And this is the period of time. And on this, then the second one, it says after 5 years. So you're going to use the compound interest formula. Again, this is the starting amount. This is your ending amount. This is your interest rate as a decimal. This is the number of times it's being compounded. And T is usually years. So anytime you see the word continuously, you know to use the PERT formula. Otherwise, you're going to use the compound interest formula. Hopefully that helps with that question. Any other problems with this homework that anyone would want to talk about? Okay, so then I just want to discuss tonight's homework. First of all, don't worry about this square root of A. So basically all this is doing is asking you to find, on this first square, you want to find log base A of 1. Hopefully everyone knows that that is what?
Zero.
Yeah.
Mhm.
And then here you would want, on the second square, you're going to want to find log base A of A. And remember, anytime your base and argument equal each other, they just cancel each other out. And what would you be left with in this case if everything cancels?
1.
Yeah. And then here we have log base A 1 over A. So what's the only difference here is that we have a 1 over A instead of an A. So what would that be?
-1.
Yes, right. So I think that's the point of this, is just to get you to see that. Then number 2, hurricanes, blah, blah, blah. What is the barometric pressure at the center of the hurricane? So hurricanes are some of the largest storms on Earth. They are very low pressure areas with diameters of over 500 miles. The barometric air pressure in inches of mercury is inside a severe hurricane at a distance of X miles from its eye or center is modeled by this. So at the center of the hurricane, how many miles away are we talking about if we're right directly at the center? What would our X be?
0.
So on that one, you're just going to plug 0 in for your X. And then here, they give you the 100 miles. So that you're going to plug 100 in. Okay, then graphing, and y'all, what I always do, and see this, we didn't really graph any. I know Matt went over it on the notes, but we didn't really graph these on the homework. So what I always do is first I graph the exponential part. So instead of graphing y equals log base 3x, I'm going to graph the inverse because it's easier for me. So the inverse of f of x equals log base 3x is f of x equals to x to the third power. I mean, yeah.
3 to the x.
This would equal to y, yeah. So this would be 3 to the y equals x, yes. So it's going to be 3 to the x, sorry. So the inverse is 3 to the x. Instead of log base 3x, it's 3 to the power of x. So I'm going to do x and y. So again, I just start usually -2, -1, 0, 1, 2. 3 to the negative second power would be 1/9. 3 to the negative first power would be 1/3. 3 to the 0 power would be 1. 3 to the first power would be 3. 3 to the second power would be 9. And so I know that this function looks like this. Okay. All you have, and I know that the asymptote is y equals 0. So now all you have to do to graph the inverse is to switch the x and the y's. And make your new asymptote what?
X equals 0.
Yep. That's it. Okay, now there's different ways you can do one like number 4, but what I would do, this is my way my brain operates, is I would first do y equals to 2 to the power of x. Then I would switch the x and the y. And change the asymptote. And what about this +6? What's that tell us to do once we've done all of that?
Move left 6 units.
What? Move
Right.
left, yes. Then move the whole thing left 6 units, right? That's what I would do. But you might like to do it some other way. So, however you do it is fine, just as long as you have the right idea.
I think probably the asymptote and the x-intercept are like the important things to get on that.
Yes, 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 yes. And you can always graph these on the calculator if you want, to see if you're doing it correctly. And base 2 logarithms, just like exponential functions, they always are going to have the same shape. So we haven't done a change of basis formula yet, so it'd be kind of hard for you to graph log base 2. But if you just did log x plus 6, you could see what's happening very easily, even if it doesn't have the correct base.
That also depends on what calculator they have, because I know the new TIs like they
They
start
do,
with-
yes,
yeah,
they
you can
do.
do odd bases on there,
Yeah.
different number bases.
Yeah, if you have the new calculator, you can go to alpha window. And then selection number 5 is the log base, but we'll talk about that more in another lesson. All right, any other questions, you guys? We did a whole lot in this hour. I'm pretty impressed that we got through all that. Did y'all feel like it was going too fast?
Not really, they're pretty good.
Okay.
Yeah, I want to stress like they really need to try these on their own.
Absolutely.
These on their own. Like,
I'd go back and do, yeah, I'd do a lot of these.
yeah, watching us is only going to get you so far, and it's not going to get you too far.
Yeah. And it's really easy when you're watching someone else do it to go, oh yeah, I know that. But
Yeah, the amount of times I heard as a tutor, it's like, if you're standing there, I can do it. But like, well, you have to be able to do it on your own for the test. So I don't know what to tell you on that one.
yeah,
But you got to practice it on your own.
yes. And if you ever want extra problems to practice with, just look at the review for this this section, and you'll see plenty of practice problems.
They also have access to the digital book.
That's
and
right.
It's got lots of practice, and it's got answers to odds in the back. So if there's any section and you're like, I don't know about this section, you can always go look it up in your book.
Yeah.
And they're usually right with their solutions.
Usually, yeah. If
Every once in a blue moon, we'll find
yeah,
one.
but
That's
it's
incorrect.
once in a blue moon. Usually, I think, oh, that's wrong, and then I figure out that I'm wrong. Now, the Maricheck book, that's not true. The Maricheck book, I think every other answer is wrong in the back, but not every other, but a lot of them.
It also depends what edition they're on. I remember
Yeah.
getting a few first
Usually
edition
they-
as a grad student or even an undergrad, I think. It's like the first edition of the book. We would like write the book publisher and be like, here's an error. Like, thank you. I'd just be like, okay, great. Oh man.
All right, you guys. Well, it's a beautiful day. I hope you get a chance to get outside and enjoy it some.
Math
Good
typos are.
And I'll hang on for anyone that wants to hang on. If anyone has any questions, I'll be happy to stay and answer them with you.
I know. I've seen a few math typos that had me spending hours trying to prove something you can't prove. That's something
always
that's
fun.
happened. Yeah.